All right, here we go, pre-algebra. We're crossing our fingers that everything will go well in this video. We're looking at 3.6% error, and this is our last topic for, or last lesson for topic 3. So today's goal, I can solve problems involving percent error. And I think you'll find that this is fairly simple and very similar to percent of change. So we're going to skip right into the key concept. And your key concept, the bottom line you need to know is that when we're looking at percent error, it's a way of describing accuracy. So accuracy is the degree to which an estimate or measurement agrees with an accepted or actual value of that measurement. So we describe accuracy with a measure called percent error. So we have a formula, of course, to help us. And our formula says that we're going to take the absolute value, so percent error is always going to be positive, and we are going to subtract the measured value or that estimated value, and from it we'll subtract the actual value. And then we divide always by the actual value. So we're really just finding the difference between the estimated value and the actual, and then dividing by the actual. So in this scenario over here, this lovely lady gets on the bus and thinks, wow, there's a ton of people on here today. Probably looks like about 36 passengers. That's her estimate. But actually, there are 45 passengers. So if we want to find her percent error, then we're going to take the absolute value of her estimated value, which was 36, minus the actual value, which was 45, and then we're going to divide that by the actual value, which was 45. So the difference between 36 and 45 is -9, but when I take the absolute value, it becomes positive. So we have 9 over 45, and when I divide that out, I get a decimal, which is 0.2 or 2/10. So this is my percent error, although it's a decimal right now and it doesn't look like a percent. So I need to multiply this by 100. So this would be 20%. My percent error is 20%. Okay, so let's look at another example. If we want to find the percent error of each estimated value, then let's start with A. I'm going to find the absolute value of my estimated value minus the actual value divided by the actual value. So I will do the absolute value of 40 minus 45, which is 5. And when I divide 5 by 45, I get 0.1 repeating. So if I want to make this into a percent, then I multiply by 100, and I get about 11%. So I'm going to round that to the nearest whole percent. For letter B, if I want to find the percent error, I do the absolute value of my estimated value minus my actual value divided by the actual value. So 63 minus 75 is a difference of 12, and the -12 becomes +12 because of the absolute value bars. And when I do 12 divided by 75, I get 0.16, and so I make that a percent by multiplying by 100. So 16% error on letter B. And finally, for letter C, the percent error, I take the estimated value minus the actual value and take the absolute value of that, and then I divide by the actual. So the difference between 125 and 99 is 26, and 26 divided by 99 equals 0.26 repeating. So as a percent, that would be 26%. So this is probably reminding you quite a bit of percent of change. So now you can pause the video and try your hand at this one. And we get a percent error of 25%. Why does the percent error formula divide by the actual value instead of the estimated value? Well, we want to find the difference between what we estimated and the actual. So if I want to find the percent that I am off of this estimation, I need to compare to the actual amount or the actual value. So let's look at a practical application. On example 2, anyone who guesses within 5% of the actual number of jelly beans in the jar is a winner. Suppose there are 486 jelly beans in the jar. Who wins? So let's first check out Sarah's work. She estimated that there were 388 jelly beans. So that's my estimation, and I'm going to subtract from that the actual number of jelly beans, and then I'm going to divide by the actual amount. So the difference between 388 and 486 is a difference of 98, and it becomes a positive 98 when I take the absolute value. So when I do 98 divided by 486, I get 0.201. So Sarah is within 20% of the actual amount. She had a 20% error. So she would not be a winner because she was not within 5%. Let's check out now Javier. Javier estimated that there are 501 jelly beans, so the estimated minus the actual divided by the actual. So the difference between 501 and 486 is 15, and when I divide 15 by 486, we get 0.030. So as a percent, we are looking at 3%. So congratulations, Javier. You are a winner because 3% is within 5%. It's 5% or less of an error. All right, let's see how Lisa did. So we'll do Lisa over here. Lisa estimated that there were 475 jelly beans in the jar. So I'm going to take my estimated value minus my actual value, find the absolute value of that difference, and then divide by the original, which is 486. So this is a difference of 11. And 11 divided by 486 is 0.022. So as a percent, we're looking at right about 2%. Way to go, Lisa. Lisa is a winner. And let's check on Jay, see how Jay did with his estimation. He estimated 450. So the estimated amount minus the actual, take the absolute value and divide by the actual. So this is a difference of 26. And 26 divided by 486 . Oh, I'm sorry. calculation error here. No wonder we're not coming out right. So 36 rather divided by 486. And J comes out to be about 7%. So J's percent of error was a little too high. He wasn't within 5%. So Javier and Lisa are the big winners. Let's check out example 3 here. Okay, we are in example 3 going to look at a dot plot, and it shows the measurements made by a science class. If the rock's actual mass is 1 1/10 gram, what is the greatest percent error among the measurements? Round to the nearest tenth of a percent. So if this is the actual measurement, then 8/10 is probably going to be where my greatest error comes from, because it is the furthest from 1.1 or 1 1/10. 1 3/10 is a little closer. So my biggest difference between the measurements is here. So I'm going to do my percent error formula, and I'm going to take my estimated value, which if the rock's actual mass is 1.1, then the estimated must be the 8/10. And I'm going to divide the absolute value of that by the actual. So the difference between 8/10 and 1 1/10 would be a difference of 3/10. And when I divide that by 1 1/10, I get 0.27 repeating. So if I'm going to round that to the nearest tenth, this would really be like 0.272727 ... So if I'm rounding to the nearest tenth of a percent, when I move my decimal point 2 spots, I'm going to drop it right here. So that would make a 27. And then if I'm going to round to the tenths place, I'm going to use the 7 to tell me to round the 2 up to a 3. So we would say 27 3/10%. Okay, so finally your turn. Go ahead and pause the video and work this one out, and then double check your answer. All right, if you got 23 7/10%, you are right. I think you are all set to check out your homework, which is digits 3.6. Good luck, everybody.